All right, so here's where we left off. We were talking about quadratic regression stuff, and I think we had covered that. And we'd started this problem, right? So a person plans to use 220 feet of fencing to enclose a rectangular garden, and we're looking for what dimensions of the rectangle would give the maximum area. Okay, and what is that area? And we'd drawn a picture. There's our garden. I guess we have a blue fence around our garden. And we had said we're going to call the dimensions of this X and Y. X is the width and Y is the depth, or whatever you want to call it. Length, or maybe X is the length and Y is the width. And so we wanted to come up here with an area function. Okay, now we know that area is equal to X times Y. Okay, and this is all looking familiar, right, from last week? Okay, so area equals X times Y, but we want area to be a function of a single variable, not a function of two variables. And this is something that's going to hold all the way through AP Calculus. And then once you get through AP Calculus, through AB Calculus, which is kind of first semester calculus, so it'd be in college. You're gonna look at some other ways you can deal with functions involving multiple input variables, right? But that's not for a long time. For now, we're really interested in being able to write this as a function of a single variable. So we want to somehow get rid of one of these two variables. Now that has to come from some other information that's given to us. And here it is right here. The fact that you plan to use 220 feet of fencing. Okay. Now, a lot of times that's a secondary equation, okay, because it's not the primary equation is the one that we're trying to work with to come up with an answer, which is area, right? They're asking us to maximize area. Now, it's really it's kind of odd that we're talking about this in here today, because I was talking about this with I got teaching 2 levels of calculus with the advanced calculus class, second year calc class. We were reviewing some of this stuff that they had done last year, and we were going through problems exactly like this, only approaching them using calculus instead of algebra. Okay, so it's really odd that these fell on exactly the same day, but they did. So when we're trying to maximize or minimize stuff, and I'm thinking, like, I'm talking to you as future calculus students here. This isn't something that's going to come up a ton in Algebra 2, but it comes up all the time in calculus. The primary equation is always the thing that you're trying to maximize or minimize. And there's a whole section called optimization. It's a big part of calculus that does just this kind of stuff. So that's the primary equation. The secondary equation is the one that's going to allow us to connect the variables and come up with a function of a single variable. Okay? Give me thumbs so far on this. I mean, we haven't done anything yet, but conceptually, are you hanging in there? Questions? Trey, you got a question? Can you ask a question for everybody? Anything to help clear it up?
Not yet. Just keep
Okay,
going.
I'll keep going. As soon as you can think of one, stop me and ask a question. Okay, now, if we were not given this other information, this would be a pretty trivial problem. I know what I would do. If we didn't have this bit up here about the fencing, in fact, I'm going to block that out for a second just to make a point. Okay, we want to enclose a rectangular garden. What dimensions of the rectangle would give maximum area? Well, as that's written right there, it's easy. I'm just going to make mine infinity by infinity, and I win, right? Without a constraint, this is kind of a ridiculous problem, because I could just make the garden infinitely big. Okay, it's when we add this other piece of information up here that now this is a doable problem, because they gave us some real world constraint. The constraint is that we only have 220 feet of fencing to use. Okay, now we got to do something. Okay, so the secondary equation oftentimes will be called an equation of constraint. because it's constraining the primary equation, okay? It limits it. So then we actually, we made some progress on this last week. We said, okay, well, what does that mean? If we have 220 feet of fencing, that corresponds to a perimeter of the rectangle, doesn't it? Right? And the perimeter of a rectangle is just 2 times the width plus 2 times the length is the perimeter, right? So we came up with the equation 2x plus 2y equals 220. And if I solve that for y, if I subtracted the 2x over to this side and divided both sides by 2, you guys told me that we came up with the equation y equals 110 minus x. Okay, I'm going to put a box around that because that's my substitution equation. I can plug that in for y, and look what we get. We get area equals x times y, but y is being replaced by 110 minus x. And so now we've got something we can deal with. My area function is 110x minus x squared. Or if I want to write that in standard form, that's just a quadratic function, right? Negative x squared plus 110x. Okay? Give me thumbs. How we doing? Okay? All right, so we want to maximize this thing. So what are we going to do? What can you tell me about that function? If I were to graph that, what would the graph look like? Let's talk about that. That's one of the most important skills in math, is to be able to take functions and think about what the graph would look like. And part of that is you've got to figure out what are the axes going to be labeled? What are they measuring here? So if I wanted to graph this guy, I'm going to make a coordinate plane, which usually would be the xy plane. Okay, what is it here? What variable is going to go on my horizontal axis? Remember, the horizontal axis is always, that's where we put the input variable. So what is it? I think I heard it. X. It's x, isn't it, right? So that part, that probably threw you off. You probably think it was going to be something different. Well, that part's not. That part's the same. Okay, what goes on the vertical axis? Say it again. A. Yeah, it's always the output, right? So normally it would be y or f of x, but in our case, it's a of x, right? So there's that axis. Okay, now what's that going to look like? That's just equivalent to saying, if we were to kind of think about this in the context of stuff we were doing last week, before we were doing these applications, that would have been f of x, or y, equals negative x squared plus 110x. Just generally speaking, what are some characteristics of that parabola? We know any quadratic function graphs as a parabola. It's opening down. That's important, right? That's really important because we're searching for a maximum. Why is that useful to us? The vertex becomes a maximum, doesn't it? Right? It's the peak, right? We want a peak, not a valley, if we're looking for a maximum. Okay, so then we can do this. What's our recipe for finding the vertex? What form is this in right here? Standard form. Okay, so what are the values of A, B, and C? Let's see. Ashley, help us out here. What are the values of A, B, and C for this function? A is negative 1. Good. B is
0. Oh, what is that? 110.
110. There you go. 110. And C is 0. There we go. Okay. So it's in standard form. Those are my parameters. Now, what's my formula for calculating H? Negative b over 2a. Okay, so if we want to put this in terms of h is equal to negative b over 2a, which is equal to negative b is negative 110 divided by 2a is negative 2. So what's that give us? 55? Okay. Everybody agree? Okay. So over here at 55, and let's just say arbitrarily that that's 55 right there, okay? We know that that's going to be the x-coordinate of the vertex. How do I find the y-coordinate? How do I do that? What's my process for finding k? Yeah, plug it in. Good. It's going to be f of h, in this case a of h, right? So it's a of 55. Okay, so that's going to give me, if I plug that in, I'm going to get negative 55 squared. And I've gone through this with a bunch of people in here. It's really easy to neglect putting the inputs when I'm evaluating a function to avoid using those parentheses. But many of you already can testify to the fact that when you don't do that, it's dangerous because you missed a problem because you didn't do that, right? On the last test. I think there was one where there was a negative number being squared, and a lot of people didn't put it in parentheses, and they got the sign wrong. As a consequence, you got to put those parentheses there. Plus 55 times 110, and what's that going to give us? Oh boy, see, 2,500. Somebody do that in your cal. I don't feel like doing this in my head. 2,500 plus 250. So would it be 6,000? Oh, not 6,000. 3,000. 3,000. Like it's gonna be 3,000, 25, 75. What is it? 25. 25. Okay. There we go. Okay. So there's the y coordinate, right? So the coordinates of the vertex then are going to be right there. Oops, I can't read that. Okay, and we know that this thing's going to open down, so we got it, right? There's our maximum. Okay. Now we were fortunate because we had a function that's only got one vertex, right? And if it opens down, we can find a maximum that way. Now, if we had a different type of function, like if this had been, let's say, a cubic function or a quartic function or something a little more exotic or some kind of a trig function, then you got to wait till calculus. Then there's really no way around. You got to use calculus. But in this case, we were able to use our understanding of how to locate a vertex to find the maximum. Okay. So then what's that tell us? We got to fill in some blanks here. So what's the width? Well, we said x was the, I don't know what you call that. We'll call that the width, I guess, right? So the width would be 55. How do I find the length? Where do I go? I'll give you a hint. I put a box around it for a reason. The boxed equation, that's the substitution equation, right? That's the one that solves for y in terms of x. Well, we solved for x. The solution for x was 55. So where do I go to find y? Right there, right? So if I plug 55 in, I get y equals 55. Is that a surprise? If I had asked you to guess what you thought the shape was going to be if we're going to maximize the area of a rectangle, what do you think you probably would have said? You thought about it a little bit. Probably a square, right? I mean, doesn't that, I bet you most people would have said a square, and you're right. A square is the most efficient way for a quadrilateral to enclose areas in a square. So 55 feet's the width, 55 feet's the length, and the maximum area would be, well, we already know what that is. 3,025, right? Because what did we graph here on this space? We were graphing area as a function of x, and so this was a maximum for area, 3,025. Okay? Okay, make sense? Now there's sometimes questions. Come up with a question? Anybody?
She was asking about 220. 220.
Oh, the perimeter. Yeah, there you go. Okay. Any other questions? Anything else? Okay, sometimes it's kind of cool to come up with proofs or arguments that have nothing to do with algebra, right? How did we know that the answer for both of those had to be 55 before we ever even plugged it back in, maybe? You have the geometric argument. If you think back to geometry, you probably talked about this a little bit. Squares are the most efficient way of enclosing volume in a quadrilateral. But what else would there be? If you think about this, is there ever any place in here where there's a distinction drawn between width and length? I mean, they're interchangeable the whole time, aren't they? I mean, look at this. What do we do here? We drew this rectangle. We put an x and a y there. We've got this equation for area. Area equals x times y. At this point, totally interchangeable. We've got this perimeter secondary equation. 2x plus 2y equals 220. Again, completely interchangeable. It doesn't make any difference, right? So should there be, how would I ever come up with a different answer, right? I mean, they're completely interchangeable. So I should come up with the same thing for either one of those, regardless of which one I choose to solve for. I could have just as easily solved for x in terms of y, and would the algebra have been different at all? No. I just would have had different variables, right? But the algebra would have been exactly the same the whole time. So I knew here, just by the symmetry of the way this problem developed, that I had to get the same answers for x and y. There were no differences. Now, if my area equation, or like if my equation of constraint had been a little bit different, what if it had been something like, arbitrarily, I'm just going to make something up, what if it had been something like 2x plus 3y equals 220? Then that would have been different, because now the x's and the y's are not interchangeable. They have different coefficients, right? So now I know, okay, they're not interchangeable. I should expect to get different answers for both of those, okay? That's a pretty high level, kind of a math theory argument, but does it kind of make sense a little bit? Give me thumbs on that. Okay, I mean, you'll talk more about that in college, stuff like that. Better get rid of this though, because that's gonna mess you up on the notes. Okay, let's try another one. How about something like this? Okay, rain gutter is made, simple rain gutters are made just from sheets of aluminum that are 18 inches wide, okay, in this case. And all we're gonna do to make a rain gutter is we're just gonna take this flat sheet of, and it's, you see that this is, I'm looking end on here, but if I wanna draw this with a little perspective, maybe it looks like this. Something like that, where it's disappearing into the distance. Everybody see that? So this is the front end, and then it's kind of going towards the back like that. Everybody get that? Kind of, right? So it's coming out of the board like this, and it's 18 inches wide. Okay, so what do I do then? I create a gutter by just bending up the edges and creating a trough that's as long as the piece of sheet metal is. Okay. All right, so we want to come up with the dimensions here that are going to allow the greatest amount of water to flow. So we're going to try to maximize the volume of this gutter. Okay? We can do that without calculus. Suggestions? What do you think? Well, we need a variable in there somewhere, right? We got to be able to come up with a volume equation. Okay? We need a variable. What's the thing I could vary about this process? And really focus on this today, because this is where some light bulbs are going to probably turn on. This will be enlightening all the way through the next few years. There's some things that are going to start. You're going to start to see some relationships. It's going to make stuff easier in the future. When we come up with a variable, it's something that we can vary. What do we have control over with this piece of sheet metal? What can we vary when we're making our gutters?
Sides.
Okay, like the length of the sides, you're calling these the sides right here?
And the bottom.
And the bottom, okay, so the length of all of those. If I know that I'm stuck with an 18-inch wide piece of metal, what am I controlling then? How am I doing that? Talk to me more about that, Carson. How are you controlling the length of the sides? Okay. Anybody want to just? I know you know the. I mean, can anybody else articulate that differently? Like, what am I controlling about this? I'm taking this piece of metal, and what am I controlling? I'm not cutting it or anything, right? What am I doing to it? What do you think, Aubrey?
You control how much of it you turn up.
Ah, okay. So where I'm making the bends, right? Okay. So let's just say that we're going to call, if I call the height of this thing X, it's going to be the same on both sides, obviously, right? It wouldn't make sense for us to have one higher than the other. The water would just spill out, right? What does that make the bottom dimension then? The whole piece of metal is 18 inches wide. What do you think, Aubrey?
The 18 minus 2x.
That's it, right? 18 minus 2x. Everybody see that? Right? Because how much have I lost out of that 18 inches? Well, I've lost the two x's that were bent up, right? Those are no longer parts of the bottom. Okay. So there's my cross section. Now, we haven't specified what x is, though, right? We've left that a variable, and that's what we want to do in math. We want to keep this general and see if we can come up with an equation that we can solve for x. So the math gods are going to tell us what value of x to pick through algebra, right? So we've got this gutter, and now it's going to be full of water. We want to maximize the volume of water that it can hold. Well, what is the thing that I'm trying to maximize here? Okay, so I'm maximizing volume, but can we make the problem a little bit simpler? Okay. Let me do one thing here. So how about right, we've got this long gutter. The length of the gutter is never going to change. Agreed? Okay. So we could call this, we'll just call this L for length. The length up from there down to there is the length. That's never going to change. When I calculate the volume of that shape of water, that's just a rectangular prism, isn't it? It's just going to be height times width times length, agreed? But the length's never going to change. What's the only thing that's ever going to change here about this? The length never does. But the way the cross sections look is going to change, right? So would you agree then that all that really matters is what the cross-sectional area is? Because the cross-sectional area times the length is going to give us the volume, right? So we don't have to bog down our calculation with a length. In order to maximize the volume, we're just going to maximize the cross-sectional area. And that's going to make the volume maximum also. Everybody get that? So that makes a simpler problem. That's something we always want to do in math. If we can trade a difficult problem for an easier problem that has the same solution, go for it every time, right? That's a good strategy. Okay, so volume is maximum when cross-sectional area is maximized. So we'll just find the maximum for cross-sectional area. That's easier to calculate. So what is the function that predicts cross-sectional area of that gutter? This is going to be this is the triangle that we're, whoops, wrong color. This is the triangle that we're talking about, isn't it? It's that triangle, or not triangle, that rectangle right there, right? That's the rectangle that we're trying to find the area of. So I think I heard it. What was it again? Oops. Somebody said it. I knew I heard it. What is it? Say it again, Trey.
18
Times x, yeah, right? Just height times length, or height times width. And so if I multiply that out, isn't that just going to give me 18x minus 2x squared? But I'm going to put it in standard form. Minus 2x squared minus 18x. And look, I can write that as a of x, right? I want to write it as a function of a single variable, okay? That is a parabola in standard form, isn't it? Or a quadratic function in standard form, yeah.
Isn't 18x supposed to be positive?
Say it again. Oh, positive, yep, you're right, positive, yep, thank you. Okay, so what are we got to calculate h and k. That's all we need is calculate h and k here. So if I wanted to put this into vertex form, first of all, let's write down the values of the parameters from standard form. What's a, everybody? -2. What's b? And what's c? 0. Okay. So then we know h is -b over 2a, which is -18 over -4, which is just 9/2. Okay. If I want to write that as a decimal, it's 4.5. Okay. To find k, I'm just going to plug that back in. And on the test, so let's talk turkey for a second here. You're going to be taking a test over this stuff. You're going to have the Desmos Scientific available the entire time. So one thing we could do when I want to evaluate stuff is take advantage of Desmos Scientific's ability to do that easily. Right? So I could, come on, what's that do? Oh, I don't know why I can't get that there. Oh well. So we're going to define a function. Right? There's our function. There's a of x. A of x equals -2x squared plus 18x. Okay, and then I want to evaluate that at 4.5 or 9/2, so I'll just go a of 9/2, and look what it does. Okay, it's telling me right over here. There we go, finally. It gives me the answer as a decimal, or if I want to, I can convert it to a fraction. Okay? So I don't even have to show that work. I can just plug that into Desmos. What was it again? 20.5? Is that what it was? 40.5? Okay? So then in vertex form, what would this thing look like? What would this look like in vertex form? And it might not be a bad idea to start off just writing down what vertex form is and then plug in the parameters that you've calculated. So what is the template for vertex form? A of x equals what? Okay, so I get a times x minus h squared plus k, right? Now I already know what a is. A is the same in vertex form as it is in standard form. That's -2, isn't it? Right? So then what do I get here? So I get -2 it was, right? Is that correct? Yep, -2 times x minus 4.5 squared plus 40.5. So what is the, let's answer this then. What's the depth of the gutter going to be that maximizes flow? What is it? If I were to think of this in terms of a graph, which is what we're trying to do here, right? If I think about this in terms of a graph, I'm plotting x on the horizontal axis and area on the vertical axis. And what are the coordinates of the vertex? Just HK, right? So what is that? What's the x coordinate of the vertex? 4.5, right? And the y coordinate? 40.5. And I know that this thing is opening down, so I got it, right? So what is the height then? We defined the height was defined as x. The x coordinate of the maximum is 4.5. And so the answer is determine the depth of the gutter that will maximize its cross-sectional area. So this part right here is 4.5 inches. And I guess that's all they ask for. They don't ask for the volume. They just want to know the depth of the gutter. Okay? Okay, how we doing? Give me 1 to 5 on it. Can we making some headway on that stuff? Okay. All right. So we'll look at a couple more examples tomorrow, and that's it. And then you got the rest of the time just to work.